Good morning on my behalf. So I'll be talking about the methods to improve the operational efficiency. Now, one way to improve, a cost-efficient way to improve the efficiency is to optimize the operation, to better plan the operations, and that's a very efficient way cost-wise to reduce the emitted greenhouse gases, lowering the operational costs, and maybe even improving the revenue, and to help do better in the global tough competition. However, planning and optimizing the operations, we would need to have current information, up-to-date information on the ship condition, how well the ship is doing at the moment, what is the level of fouling, and how the weather is affecting on the consumption. So, like we saw, by measurements, obviously we get information from the ship. We can measure the power that is put, the speed, and we have information on the weather. However, these measures might be not always available. It might be that the ship is, first of all, not equipped by adequate sensors to measure the power on the propeller, or that data is not necessarily disclosed to all of the stakeholders. The owner might not disclose his measurements to the charterer, who might be paying for the fuel and is interested in what is the actual level of performance of the vessel. Now, a noon report is a good way to gain information, and that's generally used. But the shortcoming of relying on the noon reports is that the data is quite sparse. So we have one information data point per day on the consumption, and also the weather might change during the day quite significantly, which cannot be reported in the noon report. So now, our solution to this is to use the available data, the big data that there is, taking the information from the AIS and taking the publicly available information on the ship. So what we do is that we actually build a digital twin of the vessel based on our naval hydrodynamics knowledge and expertise on designing the ships, and we make a digital twin of that vessel. So this way we can overcome some of the challenges with the sparse data of noon reports. The challenges, like I mentioned, is lying on the weather information, for instance. This is an example of noon reported weather and the actual weather, which we have interpolated at each location of the ship over several years of operation, and we can see that there is a tendency to exaggerate, for instance, the wind speeds, to mention that the speeds might have been higher than the limiting for Beaufort range. Now, these variations in weather are quite significant source of uncertainty in using the noon report as an information. For instance, here is an example of 800 days of operation of one dry bulk vessel, and we can see that during each day the swell height has varied more than 1 meter in quite many days. The wave height, the wind wave height component has varied quite a lot, and also the wind speed has varied quite a lot during the day. Whereas in the noon report we would have just one information of the wind speed was this much, and the wave height may be reported or maybe not. Now these variations in weather have quite important influence in the consumption of the vessel and also in the reduction of the speed. So already within the 4 Beaufort range, which is considered as good weather still, if we are trying to maintain the same speed throughout the weather, we need to increase 50% the consumption already in adverse weather. Or if we are operating at constant engine power, we are seeing up to 15% or down to 15% reduction in the speed. So the way that we are taking these or accounting for these challenges is that we have a full model of the ship based on our generic models, and we are taking the chart data, the available AIS data, linking it to that specific ship, and also the global weather data will be interpolated at each location of the vessel. Now we combine the noon reports there. Of course, we are also using automation signals if those are available, but here I'm presenting how to use the noon reports. And we have the digital twin, the ship model, based on the hydrodynamics models, and we have done that actually readily for the entire global fleet. So basically, we have generic models that can cover whichever ship we choose now to start into our analysis. And because we are using the automation signals from 200 vessels, we have gained knowledge to enhance our models, and we use data learning methods to improve the model. And then with that help of the digital twin, we can extract information, we can monitor the performance of the vessel, or we can do better, more exact planning of the operations. The twin that we have is based on our NAPA performance model, which is, like I mentioned, full hydrodynamic model. It takes into account the coupled effects of the wind, waves, current, shallow water, and also it has a full model of the total propulsion system. So basically, we're solving the force balances of all of these forces at the actual location of the ship, at the actual operational speed, at the actual wave conditions, and at the actual wind conditions. And we are finding the required thrust, solving the propulsion RPMs, calculate the engine power, and we get the estimate of the fuel oil consumption. So now we are not dependent anymore of just taking the samples of the days where the weather was good. Instead, we can use all of the days. Here's an example where the vessel encounters a low pressure system, and during one day the waves get significantly higher, and then during the other day the waves get significantly lower, and we can see from the AIS position data that the ship speed has increased significantly as the waves are lowering. And from the noon report data, we just get one average speed for that particular day, and we get one consumption. So normally, that consumption point is compared to the reference consumption. However, in reality, the speed of the vessel has changed almost by 2 knots, and we don't really know where that point should be located in reality in that speed consumption curve. Whereas with our method, we are calculating, taking into account each of the positions of the vessels, the reference consumption, and we assume that to be the clean hull consumption. And since it is the clean hull consumption, the increased consumption, the difference between the noon reported value is considered as being the increased consumption due to fouling. We can place that data point on the timeline, all of the data points we can use with the variations of weather, and we'll fit the increase of consumption over time. We can see here actually a maintenance during the use. Then we take the latest information, we tune the information of the performance of the vessel, and we can use that. So now that we are using all the data points, we are significantly improving the accuracy of the estimate. We can see that if we are only 3 months of operation, 3 months of data, the uncertainty is somewhere around 3 metric tons for this ship, consuming about 30 metric tons of fuel per day. However, after 10 months of operation and collecting the data, the uncertainty of the result, what is the level of fouling and level of technical performance of the vessel, is about ±1 metric ton per day. So we are getting really accurate results. So with the increased data, we increase the accuracy of the estimates, and we get better estimates. We studied a fleet of bulk containers, and this is the average improvement in the level of uncertainty over time. As we can see, that very fast we can reach this plus minus 5% uncertainty level. Now that information can be then used for estimating how much the weather has effect on that particular vessel, and also to know the current level of the vessel performance. And then that can be used to plan the operations with better accuracy. We know better the level of fouling, we know better what is the effect of weather, we can estimate more precisely the required voyage times, and we can estimate more precisely the estimated consumption for the voyages, and we can plan better what could be the sea margin level for that vessel, or for planning of different voyages or different times of the year. So it also helps in planning the maintenances. We can assess the effect also of these maintenances, so we can see how much effect the maintenances had, and we can plan different types of maintenances, maybe not only dry docking, but even lighter ones. So with this up-to-date information on the ship performance, we can do better voyage optimization to achieve more fuel-efficient operations. Thank you.